So, in this session we will be looking at teaching learning based optimization. Teaching learning based optimization is a newly proposed technique. It was proposed in 2011, right. Among the 5 techniques which we are going to see as part of this course, TLBO was the latest proposed technique. We have taken TLBO as our first meta heuristic technique to learn because we found that TLBO is much easier to understand, as well as it does not have complexity with respect to tuning of the algorithmic parameters. Unlike other algorithms, there are only 2 tuning parameters over here. So, the outline of this session is that first we will discuss the generic framework of meta heuristic algorithms. We will follow it up with the description of sanitized teaching learning based optimization. We will demonstrate the application of STLBO on a 4 variable problem, right. Then we will look into some of the common issues associated with TLBO in literature, and we will also look at some of the variants of TLBO. Before getting into TLBO, let us familiarize ourselves with the terminologies that we will be using in meta heuristic techniques and how they relate to the terminologies we have been using so far in optimization. So, for example, in optimization we were using decision variables. So, decision variables are also known as marks or subjects or position or gene depending upon the meta heuristic technique that we are working with. A solution is called as a population member, a learner, chromosome, child or parent, whereas a set of solutions are known as population, class, moths, flames, water body or swarm. The objective function value which we use in the optimization literature is also known as nectar amount or energy or fitness, depending upon the meta heuristic technique which we are working with. Fitness in particular usually means objective function value, except for few algorithms. So, in ABC, fitness does not necessarily exactly correspond to the objective function value. We will come to it later, but most of the algorithms use the terminology fitness to indicate the objective function value. So, iterations are also known as generations or cycles in meta heuristic techniques. This slide shows the communication between meta heuristic techniques and the optimization problem. Most meta heuristic techniques generate randomly a single solution or a set of solutions, right. So, when we say solutions, it is nothing but the value of the decision variables. So, if we have a problem with 5 decision variables, then we have a vector of 5 values within the bounds of the problem. Once we generate the solution, right. So, those decision variables are sent to the optimization problem, and over here the fitness function is evaluated. That is the only communication between the meta heuristic techniques and optimization problem. For every solution, right, we will get a fitness function value. So, the fitness function value is returned back to the algorithm. So, the algorithm sends the decision variables and the problem sends back the fitness function. Based on this information, the fitness and the current set of decision variables which were sent to the optimization problem, the algorithm uses intelligent operators to come up with new set of decision variables, which is again sent to the problem, and the fitness function value is received from the problem. This communication goes on repeatedly till we complete a specified termination criteria. So, if we take an example, right. So, let us assume that we have a 3 variable problem x1, x2, x3, right, and they are arranged in this order, right, that the first variable is x1, second variable is x2, third variable is x3, right. So, here phi 2 3 indicates that a value of phi has been assigned to decision variable 1, a value of 2 has been assigned to decision variable 2, and a value of 3 has been assigned to decision variable 3, right. So, now that is sent to the optimization problem. Let us assume that our optimization problem is to minimize this function f is equal to x1 square minus 8 x1 x2 plus x3, right. So, here if we see to calculate the fitness, all that we are required to do is phi square minus 8 into phi into 2 plus 3. So, if we calculate this value, it should come out to be minus 52, right, and that value is sent back to the meta heuristic technique. So, this is the only communication that is going to happen between the meta heuristic technique and the optimization problem. Broadly if we see, right, so the optimization problem could be anything. It can be even an experiment over here. Instead of this fitness function, it can be even an experiment, right, and the result of the experiment, a quantitative measure, is to be sent back to the meta heuristic technique. So, let us see the generalized scheme for meta heuristic techniques, right. So, to employ any meta heuristic techniques, we need the fitness function and bounds of the decision variable. So, that comes with the problem definition itself. So, if we have an optimization problem, we will have a way to estimate the quality of a solution In most cases it is in terms of the objective function, a mathematical expression, and the number of decision variables and their respective bounds. Right. So, the first step is to define the parameters. So, meta-heuristic techniques come with their own set of parameters which have to be provided by the user. So, for most of the technique, the two commonly required parameters are population size and maximum number of iteration. Maximum number of iteration will tell us when to stop the procedure, whereas population size is the number of solution which the technique is going to work with. So, the first step is to generate a random population within the domain of decision variables, followed by evaluation of the fitness function of this population. So, this is the place wherein we need the fitness function. Once that is done, we initialize a counter t is equal to 1 to keep a count as to how many times we are repeating the cycle. So, these are iterative techniques. So, we have a counter to keep track of the number of iterations that we have completed so far. So, we initialize t is equal to 1 and then check for this condition whether t is less than or equal to capital T, right. So, in the first place, let us say if my number of iterations is 10, so initially t is equal to 1, so it will enter this loop. This is where the technique actually starts. Now that we have a population, few members of the populations are selected. Those selected members are known as p prime, right, p prime of t. So, we already have a population, we select few members from the population, we perform some operations to them so as to vary them, right. So, the solutions which we have selected from the initial population, we vary them so as to get a new set of solutions. So, once we have the new solutions, we will evaluate the fitness function of the new solutions. So, now we have, let us say we started with a population size of 5, right. So, let us say we generated we selected few solutions from the 5 solutions and then we employed the variation operator. Let us say we came up with 3 new solutions, right. So, now we have 8 solutions and their fitness function value. We will employ a survivor strategy so that out of these 8 solutions, 5 solutions are selected, right. That would complete one iteration, right. So, we increase the iteration counter and then go and check for this condition, whether this condition is satisfied or not. So, as long as this condition is met, this cycle is repeated, and once this condition is met, we terminate the procedure, and that is the end of the algorithm. Since we have a population at any given point of at any given iteration, the best solution in the last iteration is considered to be the optimal solution determined by that particular meta-heuristic technique. So, let us see how the performance of a typical meta-heuristic technique will be. So, this is a benchmark function known as Rastringen function, right. It is a 2 variable function, it is a scalable function, as in like by varying this value of d, you can have it as a 2 variable problem, 3 variable problem, and so on and so forth. So, if we fix the value to be 2, we get this search space, right. So, x1 and x2, it varies between minus 5.12 to 5.12. So, both this decision variable have the same bounds between minus 5.12 to 5.12. This shows the contour plots. So, we have discussed in the last class what are contour plots, and this shows, the figure below shows the surface plot of it, right. So, this is x1, this is x2, and this is f, right. F is the objective function value. So, for a particular value of x1 and x2, what is the objective function value can be determined using this expression once we know x1 and x2, and that is how this plot has been made, right. So, now if we look at this plot, there are a large number of peaks. Here if you see, there are large number of peaks and there are large number of valleys. So, the job of our meta-heuristic technique is to locate the minima in this complex function, right. It does not know where the minima is. Initially we are starting with a random population. So, if it is an intelligent technique, it should be able to figure out by itself as to where the minimum solution is located and should move towards it, right. So, as we said, as we have seen in the previous slide, that these are iterative techniques. So, let us see how this will pan out. So, initially we said we will generate few solutions, right. Let us say we have 10 solutions. So, initially those 10 solutions in the search space will look like this as shown in iteration 1, and then we perform those selection, variation and survivor strategy to come up with iteration 2. So, the solution in iteration 1 and the solution in iteration 2, if we see, they have moved from their original place, and the same thing we can see in 3, right. So, this particular solution, if you see, it has come closer to 0 0, right. So, if we keep doing this for 20 iterations, this is what happens. So,
This is a typical performance of meta-heuristic technique, right? Initially the population are scattered. As the iteration progresses, they are moving towards one particular point, right? In this case, it happens that this point is nothing but the global optima, right? It manages to reach the global optima. For this problem, the optima is 0, 0. So if you substitute 0 in this objective function, you will see that you will get a value of 0 for f, right? So this is how the performance of a typical meta-heuristic technique is going to look like. That initially the solutions are to be generated and scattered randomly. We employ those 3 major steps: selection, variation, survivor. We do it repeatedly for multiple times, and the expectation is that randomly scattered solutions will converge to a particular point. It is important to remember that it is not necessary for all the points to converge, right? As long as one of the solutions in the population is converging towards the optima, it is a good technique, because the rest of the solution members can still explore the search space, right? So coming to teaching learning based optimization, teaching learning based optimization was proposed in 2011, right? It's commonly not found in regular textbooks, right? So if you want additional learning, you can look into this paper or one of these 2 papers. So all these 3 papers had proposed teaching learning based optimization. So this plot shows the popularity of TLBO. It was proposed in 2011, and ever since the number of publications citing teaching learning based optimization has been increasing exponentially. This plot shows the use of TLBO across various fields. So for example, it has been used in engineering, social sciences, business, decision sciences, mathematics, computer science, energy, material sciences, and many other fields. So TLBO, even though it is a recently proposed algorithm, seems to be gaining increased attention. So as we discussed in the beginning, we have chosen TLBO because it seems to be working on many of the problems, and it is one of the simplest techniques out there. So we thought that we will start with the simplest technique and then build on that, right? So TLBO is a stochastic population based technique proposed by Rao et al. So the inspiration for this algorithm is knowledge transfer in a classroom environment. The required parameters for this meta-heuristic technique is population size and number of iterations. So if we want to use TLBO, we need to fix a population size which is an integer, right? So basically what we mean is that we will be working with that number of solutions at any given point of time. So that is population size, and then we have a number of iteration which basically tells when to stop the algorithm. So if we look at a classroom environment, the teaching usually happens in 2 phases. One is the teacher phase and the learner phase. In the teacher phase, the students learn from the teacher, whereas in the learner phase, the students interacting among themselves and trying to increase their knowledge, right? So TLBO mimics these 2 phases, teacher phase and learner phase. In teacher phase, we will be generating a new solution, right, using the best solution available so far and the mean of the class or mean of the population. So in TLBO, the population is also known as class, right? And then we will employ a greedy selection strategy, right? So in greedy selection strategy, we will see if the new solution which we have generated is better. So if this new solution is better, we will bring that solution inside the population and eliminate the solution which was used to generate this new solution. So that is why we have the terminology greedy selection strategy. In learner phase also, we use a different variation operator to generate a new solution, right? Over here we do not rely on the best solution, whereas we rely on what is called as a partner solution. A partner solution is a randomly selected member from the class, and we will employ a greedy selection strategy. So again the same thing, that if the new solution which we generate is better than the solution which is used to generate it, then we will take the new solution. If the new solution is not better, then we will retain the current solution, right? The new solution is discarded in that case. So this is an important step in teaching learning based optimization, right? So what we are going to do is, we have a set of solution. The first solution will undergo teacher phase, the first solution will undergo learner phase, only then second student will undergo the teacher phase, right? So the first student completes the teacher phase as well as the learner phase, and subsequently the second student or the second member of the class undergoes teacher and learner phase, right? So this is the second student, this is the third student, right? So if we have 5 students, we will have T4, L4, T5, L5, that would complete one iteration, right? And we are expected to do T such iterations, right? So again in iteration 2, the first solution will undergo teacher phase, the first solution will undergo learner phase. Once that is complete, the second solution will undergo teacher phase and the second solution will undergo learner phase. So, this cycle is repeated till we complete the specified number of iterations. So, we will now see the working of sanitized TLBO on a sphere function. The objective function in sphere function is given by the summation of square of the decision variable. So, here we will take 4 decision variable, right. So, domain of the decision variable is 0 to 10. Our objective function is x1 square plus x2 square plus x3 square plus x4. So, our objective is to minimize, right. So, this function is actually a scalable function. So, instead of 4 variable problem, this can also be converted into a 5 variable problem, because the objective function is actually given by sigma I equal to 1 to d xi square. So, depending upon the value of d, this can be a 4 variable problem, 5 variable problem. We can scale this problem as we want. The first step in sanitized TLBO is to fix the population size. So, we are taking a population size of NP is equal to 5. We need to fix the number of iterations, because that is what is going to tell us as to when to complete the algorithm. So, t is equal to 10. The next step is to generate random initial population. So, the domain of the variable is given 0 to 10. We are supposed to generate 5 random solutions. So, this is solution 1, solution 2, solution 3, solution 4 and solution 5, since my population size is 5. Right. So, in this case we have generated all random numbers. So, at least for the first iteration, it is easier to calculate the objective function. So, the objective function of S1 is 80, the objective function of S2 is 40, objective function of S3 is 35, 4 is 102, 5 is 113. So, the way to calculate this objective function is f is equal to, for the first solution it is 4 square plus 0 square plus 0 square plus 8 square. So, this will turn out to be 80, right. So, similarly we calculate the objective function value for all the solutions, and this is also known as the fitness function value. So, the next phase is the teacher phase. In teacher phase we generate a new solution with the help of teacher and mean of the population. So, the teacher is the solution which corresponds to the best fitness function value. So, now we have the population and we also have the fitness function values of the population. So, from the fitness function value we can identify which is the least value, right, because we are solving a minimization problem. Once we identify the least value in the fitness function, the solution corresponding to it is the solution which has the best fitness function value. So, that solution will act as teacher. Once we have selected the teacher, we need to generate a new solution with the help of this equation. So, every member of the population is to undergo the teacher phase. So, whichever member is undergoing teacher phase, that will correspond to this x. R is a random number between 0 and 1. X best is the teacher, right, the best solution in the class or the population. TF is a teaching factor, TF is known as teaching factor, and it has to be either 1 or 2, right. X mean is the mean of the population. So, you need to remember that TF is constant for all the variables. So, if I have a 5 variable problem, even then I need to have only one scalar which has to be either 1 or 2 for generating one new solution. If we are generating a second solution, we will select TF again randomly, right. So, for one solution TF only one TF is needed, which is not the case for R, right. So, if I have 3 variable problem, then I need to select 3 values of random number between 0 to 1, right. So, R is to be selected for each variable, whereas TF is the same for all variables of a solution. Remember, this is only for generating one solution. When I want to generate another solution using teacher phase, again I need to generate TF and R, right. So, now let us apply this teacher phase for our first population member. So, this is the population member which is undergoing the teacher phase, the first population member 4008. The best solution, if we see here, it is 35, right. So, the solution corresponding to it is the teacher. So, now we have selected teacher. So, in this equation I know this one, right. Now, I need to find out the mean, right. So, mean is calculated by taking the average of all the columns. So, the average of this, right. So, in this case it is 4 plus 3 plus 2 plus 6, that comes out to 15, 15 by 5, 3. Similarly, for this column it is the summation of this, which should turn out to be 32, 32 by 5, 6.4. So, now we have mean of the class. Remember, the fitness value of the mean solution is not required, and it is definitely not the mean of this, right. So, we only require the mean solution, not its fitness. We will not spend functional evaluation trying to evaluate the fitness function of this mean solution, because we do not require it, right. So, now we need this random values and we need this teaching factor. Let us take the random values to be 0.8, 0.2, 0.7, 0.4. I need 4 values because it is a 4 variable problem, whereas I need only one teaching factor, and the teaching factor has to be either 1 or 2. Right. So, the new solution is given by this equation. So, x nu 1 is equal to this 1 indicates that we are generating a new solution for the first solution with the help of the first solution. So, this is the current solution plus the random number which we have selected multiplied by the difference of best solution and mean with the teaching factor, right. So, if we calculate this, it will come out to minus 0.80, 0.04, minus 5.46 and 4.88. So, it is element to element operation. So, for example, the first this minus 0.8 is determined by 4 plus 0.8 into 0 minus 2 into 3, right. So, the first variable is 4, the random number for the first variable is 0.8, the best solution, first variable of the best solution is 0, and 3 is the first variable in the mean, this 2 is the teaching factor. So, this should give us minus 0.8. Right. So, now we have generated a new solution. Now that we have generated a new solution, we need to find out the fitness of this function, right. Only when we have the fitness of this function, we will be able to say whether this solution is better than the solutions which we already have. So, what we will do is we will calculate the fitness function of this, but there is a small problem over here, right. If you remember, the domain of the decision variable was between 0 and 10, and this variable and this variable do not fall in this domain. The objective function is to be evaluated only for solutions within the bound. We can still calculate with these values, we can still calculate the fitness function value, but no matter how good or bad it is useless, because I cannot use this solution violates my bounds, right. So, what we need to do is first bound this solution, somehow we need to bring it back into the region. Once it is in the region, we can evaluate the fitness function value, right. So, let us see how to bound this solution. So, there can be 3 cases for bounding of the solution. The first case is given the lower bound and the upper bound, the value of a particular variable is within its bounds. So, for example, in this case it is somewhere within its bound. In this case, the variable is already within its bounds, so we do not need to bound. It can happen that the variable exceeds its upper bound. So, for example, if my lower bound is 5 and my upper bound is 10, the variable has a value of, let us say, 12, right. So, in this case it is violating the upper bound. So, since it is violating the upper bound, we need to bring it back into the domain. So, what we will do is we will push it to the boundary. So, this 12 is overridden with a value of 10, right. So, because then it comes within the bound, right. Similarly, the violation can be in the lower bound. So, for example, if my lower bound is, let us say, 3, the teacher phase can give me a solution in which this particular variable has a value of 1 as its lower bound, right. So, now the solution is violating the lower bound. So, what we will do is we will again push it to its boundary, right. So, this will become 3. So, in this example, so this is just a single variable example what I demonstrated. So, for example, consider a case wherein the lower bound is, it is a 3 variable problem 2, 3, 4, right, and the upper bound is, let us say, 5, 8 and let us say 7, right. And let us say I have a solution, I have generated a new solution which is actually 1, let us say 5 and let us say 9, right. So, in this solution, if we see this 1 actually violates the lower bound, because the lower bound for the first variable is 2. So, the corrected value would be, the bounded solution would be, x will be 2. For the second variable, it is 5, the new solution has the variable value of 5. 5 is within the bound, between 3 and 8 it lies within the bound. So, I do not need to bound it, it is already within the bound. So, 2, 5. For the third variable, the lower bound is 4, the upper bound is 7, right, but the value that I have is 9. So, in this case we will push the solution to the upper bound. So, 7, if this is our upper and lower bound, and if this is the new solution which has been generated using teacher phase, bounding of the solution will give us this. So, this bounding procedure is commonly known as corner bounding, because we are pushing the variable which is violating its bound to its particular bound, the lower bound or the upper bound. So, bounding is required almost in all meta-heuristic techniques, because the operators designed are not necessarily designed to give values within the bounds, right. There are some operators which can give you values within the bounds, but most operators do not do that. So, in that case a bounding strategy is to be used to bound the solutions. There are various other bounding strategies that can be used, but most of the algorithms use this corner bounding, right. So, again to emphasize this one, it is not the entire solution is not bounded, right. So, for example, if this is 159, it is not the entire solution is pushed to one of the bounds. So, the equivalent solution for this is not 234 or 587, right. Only the variable that is violating the bound. So, 1 is violating the bound and this 9 is violating the bound. So, only those variables are to be corrected, right. So, this is the bounding. So, now we know how to bound the solution. So, the solution which we had was minus 0.8, 0.04, minus 5.46 and 4.88, and the domain of the decision variable was between 0 and 10. So, now we can see that x1 and x3 violates the lower bound. So, I can use this operator, this max operator, right. So, what we are going to do is this, we have 0, 0, 0, 0 over here, that is our lower bound. So, we are going to compare element to element. So, what is the maximum of these two? Maximum of minus 0.8 and 0 is maximum is 0, maximum of 0.04 and 0 is 0.04, maximum of 0 and minus 5.46 is 0, and maximum of 4.8 and 0 is 4.88. So, this is our new solution. This solution is within the bounds. So, here we can see that these two variables did not violate the bounds. So, they are retained in the new solution as such, right. Now that we have generated the new solution, the next step is to evaluate the fitness of this solution, right. So, once we will evaluate the fitness of the solution, subsequently we will perform a greedy selection strategy to update the population. So, if the new solution is better, if the fitness function of the new solution is better than the fitness of the solution used to generate it, so this is Fi, so the ith solution, then the new solution will be taken inside the population, right, else the new solution will be discarded, right. If this condition does not hold, then the new solution would be discarded. If this condition holds, the new solution enters the population in place of the solution which was used to generate this new solution. So, let us now apply this to our population, right. We need to remember that we are still at solution 1, right. Solution 1 is supposed to complete the teacher phase, right. We have generated a new solution. Now, we can evaluate the fitness function of this new solution 0.04, 0, 4.88. So, if we plug that into the objective function, we get a fitness function value of 23.82, right. So, this was the solution which was used to generate the new solution, and this is the solution. The fitness of both of the solutions are given over here, right. So, since 23.82 is less than 80, this new solution is actually better, right, and this x1 is to be replaced, right. So, if I update the population, this solution enters it and this solution is eliminated from the population. So, this completes teacher phase of the first solution, right. The second step is learner phase of the first solution. Remember, we need to complete the teacher and learner phase of the first solution, only then we are supposed to do the teacher and learner phase of the second solution, right. So, that is to be taken care of, right. So, first solution teacher phase is done, right. Now, first solution has to undergo the learner phase, right. So, let us see what is learner phase. So, in learner phase a new solution is generated with the help of a partner solution. So, the partner solution is randomly selected solution from the population. So, we have a population, we will randomly select one member of the population who will act as partner to the solution which is undergoing the learner phase. In learner phase, there are these two equations which are available to generate a new solution. So, the selection of the appropriate equation depends upon the fitness function of the member which is undergoing the learner phase and the fitness function of the partner, right. So, if the fitness function of the member is better than the fitness function of the partner, then this equation is to be used, else this equation has to be used. So, the only difference between these two equations is that in one case it is you need to add this vector and another case you need to subtract this, right. So, again here R is a random number between 0 and 1. We need to generate as many random numbers as many the number of decision variables for generating one solution, right. So, if I have a 5 variable problem, I need to generate 5 random values between 0 and 1 to generate one new solution, right. So, if we want to generate another new solution when the second solution enters the learner phase, we will have to generate again 5 new random numbers, right. So, let us apply learner phase. So, we are still with the solution 1. So, solution 1 is supposed to go to the learner phase, right. Let us randomly select one of this. So, let me select that solution 4 will act as the partner for solution 1, right. So, we have solution 1 here, we have solution 4 and we need 4 random numbers. So, let these be the random numbers. Now, we will have to select which of these equations are to be applied, right. So, the fitness function of the first member is 23.82 and the fitness function of the fourth member, which is the partner, that is 102. So, between these two solutions, if we see 23.82 is better. So, if here there has to be a I, right. So, this equation is valid, right. Equation 1 is to be selected. So, if we apply equation 1, so equation 1 specifies that the new solution is current solution plus the random number multiplied by the difference between the current solution and the partner solution. So, here also it is the same thing. So, for example, this 4.88 has to be added with this number 0.5 into 4.88 minus 9, because this I am generating for the fourth variable. You can check for the rest of the 3 variables. So, it is these are element to element operations. So, this value should turn out to be 2.82. that is why this 2.82 is over here. Right. So, now we have generated a new solution. Again the same problem which we encountered in teacher phase is being encountered over here, that these 3 variables are not within the bounds of the decision variable. The bounds of the decision variable was between 0 and 10, right. So, again we will employ a corner bounding strategy to bound it, right. So, this is what it specifies. We need to bound the solution, then evaluate the fitness of the new solution and then again perform a greedy search. These steps are exactly similar to what we did in teacher phase. So, now let us employ that over here for our example. So, x1, x2, x3 violates the lower bound, right. So, if I bound them, this will become 0, this will become 0, this will remain 2.82 because it is not violating any of the bounds. So, this is our new solution. So, the next step is to evaluate the fitness of the new solution. So, it is fitness of the new solution will be 7.95. Now, we will have to perform a greedy search, right. So, the solution that is undergoing learner phase is solution 1. So, this is our solution 1, this is the new solution generated with the help of solution 1, right. So, now there is a competition between these two solutions, only one of them can survive. The one that will survive is the new solution because it has a lower fitness value than the solution which was used to generate, right. Since 7.95 is less than 23.82, this solution will enter the population and this solution will be taken out, right. So, to consolidate what happened for the solution 1 was solution 1 underwent teacher phase, it got a better solution. So, this solution became S1, right, and this solution underwent learner phase and it got another better solution, right. So, when we obtained this better solution at the end of teacher phase 1, this was removed. Now, this will be removed because we have a better solution, right. So, by applying teacher and learner phase for the first member, we have been able to reach 7.95. The best solution now is this 7.95. In this case, it happened that both teacher phase and learner phase gave us a better solution, but we could have encountered failures also. So, now let us apply teacher phase to the second solution, right. So, S2, right. So, this is S2. So, the first step is to identify the teacher. So, the teacher is 7.95 because it has the least objective function value. So, this is the teacher solution. Now, the next step is to calculate the mean of the solution. So, the mean of the population is nothing but the mean of these 4 columns, that turns out to be 2.2, 1.4, 4.4 and 5.3. 6. So, now we have the mean of the population, we have the best solution, we know the solution which is undergoing the teacher phase, right. So, now we can apply this equation to generate a new solution. Since teaching factor is required in the teacher phase, we will have to generate a random number either which has to be either 1 or 2. So, let us assume that the random number which we generated is 1, and I need 4 random numbers because I have 4 decision variables. Let the 4 random numbers be this. So, using this equation we can again generate the new solution, right. So, the new solution will be 1.02, 0.58, 5.48 and 5.98, right. In this case if we see, none of the variables are violating their bounds because the bounds are between 0 and 10, all of the variables are within the bounds. So, we can directly evaluate the fitness function of this solution. So, since the solution is already bounded, we can evaluate its fitness function, right. So, fitness function is again nothing but the objective function value. So, x1 square plus x2 square plus x3 square plus x4 square. So, that will work out to be 67.17. We know that it was the second solution which is undergoing the teacher phase, right, and the new solution it has a fitness value of 140. So, this is the solution which is undergoing the teacher phase, and the new solution which we generated has a fitness of 67.17, right. So, the new solution which we have generated is better than the old solution. So, this is better. So, we will use this to update the population, right. So, remember when we are updating the population, we need to update the decision variables as well as the fitness function value. Now, we have completed the teacher phase of the second solution. So, the next step is to perform the learner phase for the second solution, right. So, now our second solution is this one, right. So, this is the second solution. So, in learner phase, as you know, we need to randomly select a partner. So, let us select the partner to be phi, and depending upon the fitness of the current solution which is undergoing the learner phase and the fitness of the partner, we will have to select one of this equation. No matter which equation we use, we will require this random numbers as many as decision variables. So, let the 4 random numbers be 0.09, 0.7, 0.1 and 0.6. So, the solution that is undergoing learner phase is x2 and the partner is x5, 6283, and we know the fitness function of both the solutions. The second solution has a fitness function value of 67.17 and the fifth solution has a fitness function value of 113, right. So, since f is less than fp, right, f is the current solution which is undergoing learner phase, fp is the partner which we have selected. So, 67.17 is less than 113. So, we are supposed to use the first equation because of this condition. So, if we apply this equation, so this is the current solution which is undergoing the learner phase plus the random number into the current solution minus the partner, right. So, partner is the fifth solution which is 6283. We will get a new solution given over here 0.57 minus 0.41, 5.23 and 7.77. Again, if we see, these 3 variables are between the bounds, right. So, remember the bound is x has to be less than x has to be between 0 and 10, right. So, only this variable has a value which is not within the bounds. So, what we do is we employ corner bounding strategy and move this variable to its lower bound. Since it is violating the lower bound, we change this value to 0 since this value is violating the lower bound. So, the next step is to evaluate the fitness of the bounded solution, right. So, this solution is within the bound. So, we can use it to evaluate the fitness. So, the fitness turns out to be 88.05, right. So, the solution which underwent learner phase, that is the second solution, has a fitness of 67.17 and the solution which it generated is 88.05, right. So, the new solution which we have generated is poorer than the current solution, right. So, what we will do is we will discard this solution and we will retain this solution in the population. So, that is what you see over here, right. So, this value is not updated because the new value 88.05 is poorer than 67.17. So, in this case the learner phase does not yield a better solution. As we discussed previously, it is not necessary that the teacher phase or the learner phase definitely give us a good solution, there is no guarantee for it. So, this slide shows for the third member, right. So, this is the mean of the class, these are the random numbers, teaching factor, this variable is violating the bounds. So, it is brought back inside the bounds and then a greedy search is employed. So, 0, 3, 1, 5 this solution has a fitness function of 35, whereas the new solution which we generated has a fitness function of 22.47, right. So, this will be eliminated and this will be incorporated into the population, right. Then the solution 3 undergoes the learner phase, that is also similar to what we have discussed, right. So, this is the initial population. So, the solution 3, this is the solution that we are working with, right. So, in this case we have selected the partner to be 1. So, this is the partner, right. So, we have this solution which is undergoing, we have the partner, we need to compare the fitness function. The third solution has a fitness function of 22.47, the first solution which is the partner solution has a fitness function of 7.95. In this case the partner is having a better fitness function value than the solution that is going undergoing learner phase. So, we need to select the second equation, right. So, if we apply second equation, we get this new solution which is already within the bound. So, we do not need to worry about bounding the solution. So, if we calculate the objective function of this solution, it turns out to be 16.27, right. So, the solution which was used to generate this has a fitness function of 22.47 and we have obtained a solution 16.27. So, this can be eliminated, right, because I have a better solution. This solution enters in place of the solution which is discarded, right. So, this completes the learner phase of the third solution. For fourth solution, we will not show you the entire procedure, it is fairly simple and straightforward. We expect you to try it out by yourself and see if the values that we have match with the values that you have obtained. If the fourth solution undergoes teacher phase, so remember in teacher phase, to perform teacher phase we need 4 random values because we have 4 decision variables and we need 1 teaching factor which has to be 1 or 2, right. So, if we take this random numbers and this teaching factor, then you will get a new solution. You need to check whether the new solution is within the bounds or not. If the new solution is within the bounds, well and good, you go and determine the fitness function value. If the new solution is out of the bounds, you need to bound it and then evaluate the fitness function. Once you have evaluated the fitness function, you need to compare the fitness function of the new solution which you have generated with the fourth solution. So, whichever is better will be retained in the population and the inferior one would be discarded, right. So, that would be the end of teacher phase for the fourth solution, and then perform learner phase with this random number and this partner to see if you are able to get this one. Unlike the teacher phase wherein we had just one equation, here we have 2 equations in the learner phase. So, only one of the equation has to be selected. So, the equation that we will select depends upon the fitness function of the solution that is undergoing the learner phase and the partner, right. So, in this case the partner is 2. So, it has to be compared with that fitness function value and the appropriate equation has to be selected, and if you complete the calculation, see what is the solution that you are getting. Again check for the bounds, whether it is in the bounds or not. If it is not in the bounds, you need to bound the solution and evaluate its fitness function. Subsequently perform a greedy search. If the new solution is better, take it inside the population or else discard it, right. So, similar to the fourth solution, we expect you to perform the calculation for the fifth solution, right. So, the fifth solution is 6283 and it has a fitness function value of 113. So, remember for performing teacher phase, so if you use this set of random number and this teaching factor, perform the teacher phase for this particular student, the fifth solution, right. Once you perform once you generate a new solution, you will have to check whether it is in bounds or not. If it is not in the bounds, you will have to bound it and evaluate its fitness function. If the new solution has a fitness function value better than 113, you will update the population, else you will not update the population, right. So, that is what we expect you to do, determine the population and the fitness after the teacher phase. Once you have that, we expect you to perform the learner phase, right. In learner phase again you will require 4 random numbers, use these random numbers, and you will also require a partner. So, take the partner to be the third solution. So, this will be the partner solution. Similarly, if you perform the learner phase, you will get a new solution, bound it, evaluate its objective function value, check whether it is better or not. If it is better than the solution that is undergoing the learner phase, update the population, right. So, in this case either in teacher phase or in the learner phase, you will come up with a solution which will have a fitness function value of 36.39, right. So, that is why it is updated in this population. To consolidate, we had 5 solutions, right. So, the first solution underwent teacher phase followed by the first solution undergoing the learner phase. Only when the first solution had completed teacher phase and learner phase did the second solution undergo teacher phase. Similarly, we performed for all the 5 solutions. So, once this is complete, we have completed one iteration or one generation or one cycle of TLBO. This has to be repeated multiple times. Remember the generalized structure of meta-heuristic techniques that we discussed some time ago. So, this procedure has to be repeated multiple times. How many times? T times. T was a user defined parameter which we had fixed at the beginning of solving this example, right. So, here if we see at the end of 10 iteration, this is what the solution would look like. By now you would have realized that no doubt whatever we were doing was very simple, basic arithmetic operations is what we were performing, but there are way too many computations, right. So, usually these techniques are useful only when we use them implemented on a computer, because it is too difficult, too laborious I would say to implement these many iterations for these many population size. So, in this example we had taken a population size of only 5, right. If your number of decision variables are large, then we would work with a larger population size and we will have to perform many iterations, right. So, it is very difficult to fully realize the potential of meta-heuristic techniques if we do not use a computer. So, coming back to this problem, right. So, at the end of 10 iterations, this is the population, right. So, in this population if we see 2 solutions have reached an identical value, identical objective function value of 0, and their decision variables are also identical, right. So, now since we have performed the required number of iterations, we will consider 0 to be the minimum of this function. In this case it happens that 0 is indeed the minimum of this function, but TLBO does not guarantee that we will always reach the global optimal solution, right. The expectation is that it will reach, but it may or may not reach the globally optimal solution. So, let us see what was actually happening during the iteration. Since we performed only one iteration, it is difficult to see how things were panning out, right. So, this is a video which was generated using a MATLAB program. We have taken a 2 variable problem x1 and x2 with a lower and upper bound of -100 to 100, that is the lower and upper bound for both the variables, it is the same, right. These points which you see on the right hand side are the solutions, right. Initially we generated a random solutions, right. So, those are plotted over here. So, as iteration progresses, these solutions would move, right. So, when let us say if this is let us say solution 1. So, when solution 1 underwent teacher phase, it would have changed, and when it underwent learner phase, it might have further changed, right. So, these solutions are going to keep moving in this search space, right. So, this is the search space, these lines are our contour plots. This plot shows the search space and this plot shows the objective function value, right. So, if I run this video, right. So, here you will see the solutions are moving, right. So, the solutions are trying to converge to a particular point, right. So, see all the solutions are moving towards one particular point, right, as my iteration progresses. So, as iteration progresses, all the solutions have converged to a particular solution, right. So, same thing if you see on this plot, right. So, here we have the objective function value which is continuously decreasing. Initially when we started, we had an objective function value of more than 500, and now it has converged to 0. So, this shows the working of TLBO. Let us consolidate whatever we have seen it in terms of a pseudocode, right. So, pseudocode is a simple representation of whatever we have discussed so far, right. So, the first thing was we had to provide the input fitness function, the lower and upper bounds. So, this comes from the problem definition. We had to fix the population size and the termination criteria. Then we initialized a random population, let us call that random population as P. After generating the initial random population, we evaluated its fitness, right, fitness in the sense we evaluated its objective function value. We decided to do something for t times. So, this is that loop for I is equal to 1 to t, and for each iteration, right. So, that is the iteration loop, and for each iteration every member of the class was supposed to undergo the teacher phase as well as the learner phase. So, this for loop is going to take care of that fact. Within this second for an end is going to repeatedly happen for every member, right. So, for every member we determined the best solution from the population. So, that was the teacher, we determined the mean of the population and then we found a new solution using this equation. The new solution may or may not be within the bounds. So, we bound the new solution and then evaluate its fitness function value. Once we evaluate the fitness function value, now we are in a position to compare the solution which was used to generate the new solution. So, the solution which was used is x of I, right. So, we will accept the new solution if it is better than xi, right. So, that would complete the teacher phase. So, this block indicates the teacher phase. In the learner phase, for every member we had to select a partner, a random partner. So, xp is the partner. So, we had to decide which is the equation to be used, right, depending upon the fitness function of the solution which is undergoing the learner phase and the partner solution, right. So, depending upon that we had to decide on this equation and then we will be able to generate a new solution. Once a new solution is generated, we bounded that new solution. We bound those variables which are violating their domain constraints and then we evaluate the fitness of the new solution. So, now we have a new solution, just like teacher phase, we have a new solution, we have its fitness, we have a solution which underwent learner phase and we have its fitness. So, we perform a greedy search over here and accept the solution whichever is better, right. So, this shows the entire procedure which we have been discussing for past some time, right. So, this is a pseudocode of TLBOs. Algorithms are very often evaluated on the basis of the number of times we evaluate the fitness function to reach the optimal solution, right. So, if you have seen every time we generate a new solution, we go and evaluate the fitness function, right. So, the question is, if I am doing t iterations, right, with a population size of NP, how many functional evaluations am I doing, right. So, that is what we are going to evaluate now, right. So, if we see there are three places wherein we are evaluating the fitness. Here we are evaluating the fitness, here we are evaluating the fitness and here we are evaluating the fitness, right. So, when we evaluate the fitness here, we are evaluating the fitness for the entire population, right. So, if my population size is NP, we will be doing NP evaluations of the fitness function, right, whereas here in both these places we are evaluating only once, right, only once for a particular member. This is inside the loop. I am not estimating, as of now I am not estimating the total number of fitness function evaluation, right. I am just saying that for one particular solution, how many fitness function evaluations are required in teacher phase and learner phase. So, one over here and one over here. Since we are going to do this for NP populations, it will be 2 into NP, right, because I have 2 per member. So, if I have NP members, I require 2 NP fitness function evaluations and this I am going to repeat for T generations, right. So, the total number of fitness function evaluation is 2 into NP into T. So, that is inside this algorithm loop. I also spent NP functional evaluations at the beginning to estimate the fitness function of the random population. So, that is within this iteration we have 2 NPT functional evaluations, right, and I had also spent NP functional evaluations over here. So, the total number of functional evaluation is this 2 NPT which is consumed during the iteration and this NP functional evaluations which I spent for evaluating the initial functional evaluation, right. So, this is the total number of functional evaluation. So, if you specify NP to be 5, right, and if you specify T to be 10, right. So, I do not need to actually run the algorithm to find out how many functional evaluations would be required, right. So, this will be NP 5 plus 2 NPT. So, 2 into 5 into 10, right. So, NP is 5, 2 NP 10. So, the total number of functional evaluations is, so this is 10, 100, 105. Right. So, this is how we evaluate the total number of fitness function evaluation. So, now that we have understood TLBO, let us see how well it fits into the generalized scheme which we have started with. So, remember in the starting of this session we had discussed the generalized scheme for meta-heuristic techniques, right. So, let us see how well TLBO fits into this. So, defining parameters, we had to do that in TLBO, right. We had to fix the population size and the maximum number of iterations. We generated a random population, we evaluated its fitness function. So, all these 3 steps which are there in the generalized scheme was also there in TLBO. So, we had to initialize the number of iterations, right. So, we did something repeatedly for t iterations, though we showed it only for the first iteration, right. You are supposed to do it for multiple iterations, so this seems to be okay, right. So, this selection operator, if you remember, we did two types of selection. One was we selected the best solution in the teacher phase, and then we had selected a partner solution, right. So, that can be said to be fit into this selection phase. So, it is not necessary that I select a specified number of solutions. So, that is the beauty of meta-heuristic techniques, that in TLBO we are only selecting the best solution and the partner solution, right. So, in some other meta-heuristic technique we may be selecting a more than let us say 5 solutions or more than 10 solutions from the solution pool. So, it varies from technique to technique, but basically I did have some kind of selection operator, right. And then if you remember, we had these 3 equations, one equation in teacher phase which involved the teaching factor, right, and then I had this one equation in my learner phase, like there were 2 equations, but one of the equation is valid for every member depending upon the fitness function, right. So, I varied those solutions to get new solutions, right. So, this variation also happened, right. So, once we generated new solutions in TLB also, we bounded them. If it is not within the bounds, we bound the solution. So, the bounding can be considered as part of variation itself, right. So, then we evaluated the fitness function, right, of the new solution. As and when we evaluated the fitness function of the new solution, here we employed a greedy selection strategy, right. So, we said like between the solution which is used to generate the solution and the solution which has been generated, one of them will survive based on their fitness function. So, this also is valid in TLBO. So, we can see that TLBO fits well into this meta-heuristic techniques, and as we progress we will see that rest of the techniques also more or less fit into this framework. So, now we have completed the study of teaching learning based optimization, the algorithm. Let us see how do we represent results from this algorithm, right. So, we have various type of convergence curve. The one that is probably the most widely used is a curve between the number of iteration and the best fitness function value. So, how do we plot it? Let us say at the beginning my population was P0, right. These were the solution value of decision variable x1 and x2, right, and these are their corresponding fitness function value or objective function value. So, what we can do is we can make a plot, the x axis iteration and the y axis is the best fitness function value, right. So, among these 3 solutions, if we see 208 is the best solution. So, I am going to plot that particular value alone. I am not going to plot 277 or 397, only the best value in the fitness function is plotted. Right. So, then subsequent to this we perform the teacher phase, the learner phase, and at the end of iteration 1, let us say this is our population and these are their corresponding fitness function value, right. So, in this at the end of iteration 1, the least value is 116 in this, right. So, I retain the first point because it corresponds to my iteration 0, and at the end of iteration 1 I had 116. So, we have plotted that 116 and we continue doing so. So, at the end of iteration 2, let us say this is the fitness function value, the best value here is 68. So, we plot that 68 over here and then we keep doing it and say at the end of iteration 10 we have this fitness function value, right, 0, 0, 1. In this the least one is 0, it does not matter whether you take this 0 or this 0, right, we are not plotting the solutions, we are plotting only the fitness function value, right. So, this will look like something like this. So, this is called as the convergence curve. So, this curve shows you that as iterations progressed, how much improvement we were able to do in the objective function value. In this case, it seems to have converged to the global optima, right. So, there is not much change or at least visible change in those 3 values. So, this curve tells us the performance of the algorithm as iteration proceeds, how we are improving in terms of the best solution that we have. So, now we look into some of the issues in implementation of TLBO, right. So, as we have shown you earlier, TLBO was proposed in 3 different papers, right. So, this one is from Information Science, it was published in January 2012, right. So, subsequent to this a paper came in December 2012, so the same year in the same journal Information Sciences. So, this paper reported some of the issues with this paper, right. Broadly there were 2 issues. One is that the number of functional evaluation was not estimated properly. So,
this paper reported that the number of functional evaluation has to be what we discussed earlier, 2 NPT plus NP, right. So, before that it was not calculated as this one, but something else, right. Additionally, there was another step implemented in teaching learning based optimization called as duplicate removal. We will look into that. When we have duplicate removal, we will actually substitute a new solution instead of the duplicates, that also consumes functional evaluation. So, that was not considered in this paper, right. Apart from that, there was this issue as to when teacher phase and learner phase is to be implemented, right. So, subsequent to this paper, another paper appeared in 2013, April 2013, which kind of criticized this paper, right, stating that the conclusions drawn in this paper are correct. What we are trying to show you over here is that these techniques are extremely simple, but it is necessary to give a exact description of whatever has been proposed, right. So, as we will see, the teaching learning based optimization in this paper does not clearly specify how the teacher and learner phase are to be implemented. Very often one way to resolve this is to look into the implementation. Many authors have started to provide their codes, right. So, it is always a good idea to have a go and have a look at the codes, because it is the codes which ultimately would have generated the results. Ideally, there should not be any mismatch between what has been described in the paper and what has been implemented in the code. So, this is the flow chart that is given in one of the paper, right, one of the original paper which proposed TLBO. So, here if we see, the first step is to initialize the number of students and the termination criteria, which is fine enough, and then it says calculate the mean of each design variable. So, each design variable over here means each decision variable, identify the best solution, which is the teacher, generate a new solution as per this equation. If the new solution is better than existing, then we have to accept it, right, and continue. But if the new solution is bad, then we have to reject it over here, and then there is no connect how to, if we reject it, how do we proceed forward, right. So, assuming that it is, even if we reject, it is to be, we need to go over here, right. Then we need to select any two solutions randomly. So, here is where the learner phase is being implemented. So, we compare the fitness of the current member and the partner, right. Depending upon which one is better, we select either this equation or this equation to generate a new solution, and then again we perform a greedy selection over here, right. So, whatever is the better solution, we accept that solution, and then we check for the satisfaction of the termination criteria. If the termination criteria is satisfied, we stop the algorithm, else we go back over here, right. So, over here if you see, I can interpret this flowchart in two different ways, right. First one is this one, that for every iteration, right. So, for I is equal to 1 to NP, we will perform the teacher phase of ith solution, we will update the population, perform the learner phase of the ith population and update the population. So, this is one way to interpret this flow chart, because it does not exactly specify this for loop, right. This loop which you see is the iteration loop, right, because it talks about the termination, satisfaction of the termination criteria. We check for this criteria at the end of the termination, right. I can also interpret this flow chart in this way: for I is equal to 1 to NP, perform the teacher phase of the ith solution, update the population, end. So, in this case, all the members first complete the teacher phase, and then I have for I is equal to 1 to NP, we perform the learner phase of the ith solution, update the population and end. So, all the learner phase is over here, right. So, here it is T1 L1, right. So, here all the teacher phase are completed. If I have 3 members, the teacher phase of all the 3 are completed and the learner phase of all the 3 members are implemented over here. Whereas, here the first member will complete the teacher phase, the first member will complete the learner phase, then the second member will undergo teacher phase, the second member will undergo the learner phase, the third member will undergo the teacher phase and the third member will undergo the learner phase. So, this is what we have discussed previously. But since this flow chart is not clearly given, right, it does not explicitly state where to start the teacher phase and where to end it. So, this anomaly arises over here, right. So, whatever we have seen is this one, that in iteration 1 a member will complete teacher phase, will complete learner phase, only then the second member will undergo teacher and learner phase. This is how the code of TLBO is, right. So, in one of the later papers they have also given the code of teaching learning based optimization. So, in that case this is how it is implemented, whereas if you look at the example given in the paper, right, it employs this strategy, right. So, if I trust the code, then I need to call this as the true TLBO. If I look into merely into the paper, this is the implementation of TLBO, right. So, that is because it is not clearly described as to when to begin the teacher phase and when to complete it, and similarly when to begin the learner phase and when to complete it. So, this is exactly the same thing what we have discussed previously. This is the flow chart and this is the pseudo code which we have discussed, right. So, here if we see, we start the population loop over here, right, and here we complete the teacher phase, right, and we implement the learner phase over here. So, the second member can undergo teacher phase only when the first member has completed the teacher phase as well as the learner phase, but it is not difficult to implement the other version, right. All we need to do is over here we need to write a end, right, and then we need to begin another loop for I is equal to 1 to NP. So, if you look at the codes, you will get both types of codes, right. One is wherein the teacher phase, learner phase of every member is completed before the next member begins, right. This is what we have discussed, but if we implement, if we just put an end over here and begin another for over here, it becomes T1, T2, T3, L1, L2, L3, right, in every iteration. So, this is one of the issues in implementation of TLBO, right. The other one is the removal of duplicates, right. So, the description of the TLB algorithm does not mention the removal of duplicates. First, let us try to understand what are duplicate solutions. So, two solutions with identical set of decision variables are said to be duplicates, right. So, if I have a two variable problem, let us say x1, the solution x1 is 2, 3 and the solution x2 is also 2, 3, right. Then x1 and x2 are duplicates, obviously the fitness function value of x1 and x2 would be identical. So, these are duplicate solutions. However, the solution x1 is equal to 2, 3 and the solution x2 is equal to 3, 2 are not identical, right. Depending upon the fitness function, they may or may not have identical fitness function value, right. So, here we have given two solutions, let us say solution 1, solution 2, the values of the three decision variables are 2, 5, 4 and here it is 4, 2, 5 and the fitness function is x1 minus x2 minus x3. So, if we calculate the fitness function of this first solution, it will turn out to be minus 7 and for the second solution it will turn out to be minus 3. Since the fitness function values are different, we cannot call S1 and S2 as duplicates. However, if we sort both the solutions, so if we sort the solution, it will become 2, 4, 5 and the solution S2 will also become 2, 4, 5 and their fitness function would be identical, right. So, when we are comparing the solutions, right, the solutions should not be sorted and then compared. So, the value of decision variable 1 over here should be compared with the value of the decision variable over here. Similarly, the second variable has to be compared and the third variable has to be compared, we should not sort. However, the TLBO code which has been given by the authors actually sorts the solution, which is incorrect. So, here S1 and S2 are not duplicates. However, if S1 had been 2, 5, 4 and if S3 another solution had been 0, 5, 2, right. So, both of them have fitness function value of minus 7, minus 7. So, in this case I cannot call both of this as duplicates, these are realizations. So, duplicates are when two set of solutions are identical, the decision variables are identical, again without sorting, right, those are duplicate solutions. So, now if you look at the equations, right, so the new solution which we are generating in teacher phase or in the learner phase, we have this random numbers which we are generating, and since we will be generating them on a computer usually, those random numbers would be definitely be different, right. So, it is very rare for us to come across duplicates, especially if our problem dimension is high, right. So, now the question is, should we remove the duplicates, right. So, to remove the duplicates we will have to first identify the duplicates and then have a procedure to remove them, right. So, if you remove one particular solution, we again need to substitute it with some other solution, right. So, one is the identification of the duplicate solution, and the second is the computational time that is required for this purpose, right. But if the frequency of duplicates occurring itself is low, then we need not remove this duplicates. So, most algorithms do not employ this duplicate removal procedure, right, because it is extremely rare for two solutions to be identical, given that we will be working with some 16 decimal. So, to consolidate, the difference between TLBO and STLBO is that duplicate removal is included in TLBO, right, and the problem is that the duplicates are identified by sorting the solutions, which is not the definition of duplicate, right. So, that is one problem with TLBO. So, in sanitized TLBO, we do not have any duplicate removal procedure. This is consistent with the other algorithms which we will be discussing as part of this course, right. So, the second thing is the number of times the fitness function is evaluated, right. So, in sanitized TLBO, we have seen this expression that this is unique, right. As long as we fix NP and T, the number of fitness function evaluation is deterministic and it can be determined. Whereas in TLBO, that is not the case, because it then depends upon how many duplicates we encounter. For every duplicate solution that we will encounter, we will generate a new solution. So, if we generate a new solution, we will also have to evaluate its fitness value, right. So, a priori it is not possible to say as to how many duplicates will be generated, right, and the number of fitness function evaluations will depend on how many duplicate solutions we generate. So, another difference between TLBO and STLBO is that how do we identify the partners, right. So, in TLBO it is perfectly possible that more than one solution have the same partner, right. So, if we have let us say 5 solutions S1, S2, S3, S4 and S5, right, then S1 and S5 can have the same partner S2. So, every time it is randomly selected in TLBO, whereas in STLBO we ensure that every member has an unique partner. So, each member S1, S2, S3, S4, S5 will be partner for one solution or the other solution. So, each solution will get an opportunity to be partner to one another solution. So, that is what is STLBO. So, we do not employ duplicate removal. Since we do not employ duplicate removal, the number of fitness function evaluation is deterministic. Given the size of the population and the number of iterations, we can determine a priori as to how many functional values will be required, and in sanitized teaching learning based optimization, every member gets to be a partner to some other solution, right. Now, let us look at couple of variants of TLBO. So, TLBO, as you know, was proposed in 2011. Subsequent to that, there have been a large number of variants which have been proposed for TLBO. We will briefly touch upon two variants of TLBO. One is elitist TLBO, known as ETLBO. So, what is done over here is, in every iteration we will identify the worst solutions and we will replace it with elite solutions. So, in every iteration what we will do is, we will sort the fitness function value 2, 3, 5, 8, 9, 14, 17, something like this, right, and we will fix an elite size, right. So, what we will do is, we will save this 2 and 3 in some other variable before we begin that iteration, right, and at the end of the iteration we will replace the 2 worst solution, right. So, if the elite size is 2, then we will replace the 2 worst solutions with the 2 best solutions. So, that is what is done in ETLBO. So, it is incorporated in every iteration at the end of learner phase. Otherwise, the procedure to generate new solution is the same as in TLBO. So, in this case, the algorithmic parameters are population size, number of iterations and elite size. So, the user is also supposed to give the elite size, right. So, even in ETLBO, duplicate removal is performed, but after replacing worst solution with elite solutions. So, in improved teaching learning based optimization, the population is divided into subgroups, right. It incorporates tutorial learning and self learning in teacher phase and learner phase respectively, right. So, this basically means that whatever equation we had, there are couple of more terms to those equations, right. So, if you are interested, you can go and have a look at this paper, it gives the details about this. Here for this course, we are actually restricting with only teaching learning based optimization. Just to give you an overview about the developments, we are discussing these two variants, but our objective was to learn only teaching learning based optimization. That is why we are not doing this improved teaching learning based optimization in greater detail, right. Coming back to improved TLBO, right. So, here we do not have one teacher, but we have a number of teachers which equal to the number of groups. So, if we have a population size of 100, we may decide to have 5 groups, right. So, there will be 5 teachers corresponding to each group, and there will be a chief teacher. So, chief teacher is the best solution in among all the 100 solutions, right. So, the remaining teachers are selected based on their fitness value and the fitness value of the chief teacher, right. In addition to that, an adaptive teaching factor is introduced in improved teaching learning based optimization. Additionally, the concept of elitism and duplicate removal is also incorporated in improved TLBO. So, the codes of TLBO are freely available, right. In the subsequent session, we will also implement TLBO on MATLAB, right. So, as invented by the inventors is available over here, right. So, this is the website of Professor Rao, right. You can go and have a look. You will be able to see that it includes duplicate removals. You can also see how duplicates are actually identified after sorting, which is not correct, right. So, you can download the sanitized TLBO from this link, right. So, over here we employ this strategy that T1 L1, T2 L2, T3 L3 and so on. So, the first member completes the teacher and learner phase, only then the second member undergoes teacher and learner phase, whereas the MATLAB code over here, in this case all the members complete their teacher phase first, right, and then all the members undergo learner phase. So, for an arbitrary problem it may not be possible to say which one will work, which one will give better results, right. So, but both versions are available, and a Java code is also available at GitHub, right. So, you can download any of these resources and use it. So, some additional reading is given over here, right. So, this is the information science paper by in which TLBO was proposed, right. So, this is again a note on teaching learning based optimization which criticized this paper. This is comments on a note, so which criticized this paper, right. There is a book on TLBO by Professor Rao, right. So, you can have a look at it, teaching learning based algorithm and its engineering applications. A survey of teaching learning based optimization is also available. It was published in 2019, right. So, teaching learning based optimization has also been extended for solving multi objective optimization problem, right. So, you can go to this journal, engineering applications of artificial intelligence, and have a look at it if you are interested. In this session, we saw the generic framework of meta-heuristic algorithms. We then learnt what is sanitized teaching learning based optimization. We showed you the working of sanitized TLBO on a 4 variable optimization problem. We then discussed some of the issues which are there in TLBO, right. So, for example, duplicate removal, how do we identify duplicates, right, all those things we discussed. We then looked into the 2 variants of TLBO, elitist TLBO and improved teaching learning based optimization. With that, we will end this session. In the next session, we will implement teaching learning based optimization using MATLAB. Thank you.